one of the first topics we generally talk about in a calculus course is the concept of a limit. The idea of what's happening to the function's value as we get closer and closer to the input or the x value. So a quick little kind of idea for a picture here. Let's say that we have some function going through here, let's say f of x, and we're heading towards some value here. What is that value of the function as we get closer and closer to this x value? Now there's a lot of ideas squeezed into that one little thing, and we got to take a look at it. But first, let's take a look at what the notation is. When we're talking about a limit, here's what it looks like. We use LIM for limit. Right below it, and so this would be like on the line that you're writing. Right below it, we'd say, come on, the limit as x approaches c of f of x. So this is the limit as x approaches c of f of x. So the limit as x approaches c of f of x, the arrow's red as approaches. So the question is, what's happening to this as our inputs get closer and closer to c? Well, that's worded as one question, but it's really two questions embedded into one. Because if we approach c, if you think about this on the x-axis, we can actually approach c from two different directions. We could use values that are less than c but are getting closer and closer to c. Or we can use values that are bigger than c and approach c from that way. They're getting smaller and smaller heading to c. So really, there's really two limits inside this one question. This is generally called a full limit. We also have what's called one-sided limits. Now, one-sided limits, we're only concerned as we come from one direction. So here's the way that we would do it. This is the limit as x approaches c, let's say, with a plus sign from there of f of x. This is from above or the right. Either one of those would be correct. Or we can do the limit as x approaches c with a little minus sign there, means from below or from the left. So let's say if we did the first one, the limit as x approaches c from above, that means that we would use values that are getting closer and closer to c, but from values that are bigger than c. And if we were using the limit as x approaches c from below or from the left, we'd be using values that are less than c heading this way. Now, for a limit to exist, the limit from the left has to equal the limit from the right. So basically, these two limits have to exist. So here's what we say. We say if the limit as x approaches c from below of some function equals the limit as x approaches c from above of some function, let's say that's some value. Let's call it L. That's normally a number like 7, 8, something. If this is true, then what we say then the limit as x approaches c of the function is L. So like I said, this one question, what's the limit as x approaches some value of f of x, really has two questions embedded in it. What's the limit from the left and the limit from the right? Well, if those end up being the same thing, then the answer is whatever the value is there. So let's take a look at a more specific example. So let's say we have a picture that looks like this. And there's our f of x. And let's say that this is 2 and 8. So if I were to ask you the question, what is the limit as x approaches 2 of f of x? Well, like I said, there's really two questions buried in this one question. We need to say, well, what is the limit as x approaches 2 from above? And what is the limit as x approaches 2 from below? We got to figure out those two values first. All right, let's start with from above. So let's say we pick values bigger than 2. Now, since we're approaching, technically what we mean is we're getting infinitely close to it. So if I'm going to pick a value bigger than 2, something like 20 is bigger than 2, but we want to be really close to 2. And what does really close mean? Well, in math, we don't have a definition for what really close means. So you just say, so like, what would 2.1 be? What would 2.001? 2.0001? So we're getting closer and closer. Would you agree, as we pick values that are slightly bigger than 2, as we move towards 2 this way, these y values are heading down. And they're heading down towards a what? A y value of 8. So as we approach 2 from above, from values that are bigger than 2 head this way, these guys here are actually heading down the graph, and they're heading down the graph towards 8. If we pick values that are less than 2, or from the left, we would pick values over here, so like 1.9, 1.99, 1.999. So we're walking towards 2 this way. You can see that the corresponding y values on this side are heading up. And what? They're heading up towards a y value of 8. So since the limit from the right is the same as the limit from the left, we can say that this limit exists. And not only does it exist, we say that the limit is that value. Okay, so from a picture, we can actually tell whether or not a limit exists just by looking at the limit from the left and the limit from the right. So let's take a look at another picture. We need a couple more pictures here. All right, let's say, what if we have a picture that looks like this? Let's say that that's 5. There's our function f of x, and let's say that that's 3. Okay, so here we have a graph. What would we answer if we said, what is the limit as x approaches 5 of f of x? Now again, anytime we're doing a limit, there's really 2 limits hidden in it. So we need to do the limit as x approaches 5 from below, and the limit as x approaches 5 from above of this function f of x. All right, so from below, that means we're picking values smaller than 5. So we're heading towards 5 along the x-axis this way. So we're walking this way. And you can see for each one of those, the y values are actually heading down towards a y value of 3. But unfortunately, notice there's a hole in the graph right there. That means that this graph does not exist at x equals 5. However, since approaches means getting closer, that means we never actually get to 5, which means these points never actually get to 3, right? They're coming down, they're getting closer and closer to 3, but they never actually reach 3. So for a limit to exist, the graph doesn't even have to exist there, right? Because we're just getting closer and closer to 5 this way, which means we're getting closer and closer to the y value of 3 this way. So the limit as x approaches 5 from below here is 3. Same idea, if we're approaching 5 from above this way, you can see that the y values here would be heading up towards a y value of 3. Again, since we never get to 5, we never actually get to that place that doesn't exist, but it is heading towards 3. So here, since the limit from the left is the same as the limit from the right, we can say that this limit exists and that that limit is 3. All right, let's take a look at another graph, because these can get pretty ugly looking. Okay, what if I had a graph that looks something like this? And let's say that that's 1, 2, and 3. Again, let's call this function f, just for fun, and if I were to ask you, what is the limit as x approaches 1 of this function? So we're approaching 1 on the x-axis. What's happening to the y-axis? Again, anytime we have a limit, we're really looking at 2 one-sided limits. Let's do the limit as we approach 1 from below of the function, and the limit as we approach 1 from above of the function, and see what we end up with. All right, let's start from below. So if we're heading towards 1 from below, we're coming in from this left-hand side, we're walking along the axis, we're walking towards 1. You see the y values are heading up here, and they kind of turn around. It looks like they're kind of heading down, kind of towards 3 there is what it looks like, right? As we head this way, the graph's heading up, and it looks like it's turning back down and heading towards 3. So I'm going to say 3. As we head towards 1 from above, we're walking this way along our x-axis. We're heading towards 1, and you can see the y values here are heading down this way, and they're heading towards a y value of 2. All right, so notice we have both one-sided limits exist. The limit from the left exists and the limit from the right exists. However, since they're not the same value, we say that this limit does not exist. So here we would say that this does not exist. Now you can abbreviate this, of course, as D and E, does not exist. Okay, so for a full limit to exist, the limit from the left has to exist, the limit from the right has to exist, and they have to be the same value. Here they both existed, but it went to two different places, so this function does not have a limit at x equals 1. All right. Now there's another method that's far less used, but can be helpful. It's called a numerical way. That was just looking at the graph. Numerically, let's say that I gave you a function like this. F of x is, let's do x squared minus 9 over, I don't know, x minus 3. And I want to know what is the limit as x approaches 3 of this function. Now you'll notice this thing doesn't even exist at 3, right? We're not allowed to plug 3 into this function because we'd have a 0 in the denominator. So one way that we could do this is we can make ourselves a table. Now, generally you're going to need a calculator for this, but let's start like this. Here's what I'm going to do. The first one is going to be our x values, and then this is going to be evaluated there. Now, we want to know what's happening at the x value of 3. We don't know, right? So what we're going to do is we're going to think about this as a limit. So I probably didn't give myself enough room right there. So we want to pick values less than 3. So like 2.9, 2.99, 2.999. Over here, slightly bigger than 3 would be 3.1, 3.01, 3.001. Now here's where a calculator is going to come and play quite a bit. What you're going to need to do is you're going to need to take each one of these values and plug it into here and see what you get. I'm going to help you. If you do this in a calculator, that's going to give you 5.99999. Over here, this is going to be 6.01, 6.01, and 6.1. So by looking at this, what does it look like it's heading to as we come in from this direction? It kind of looks like that's heading bigger and bigger and bigger and heading towards 6. As we're heading this way, it's actually getting smaller and smaller and smaller, but that also looks like that's heading towards 6, which means we can conclude that the limit to this is most likely 6. Now, the problem with this method, by the way, this is a good way to kind of tell, get an idea of what's going on, is we didn't get infinitely close. Like from a picture, we can see that nothing weird happens as we get really, really close to 1. Over here, when we get really, really close to 3, what if it had 2.9999999, all of a sudden the graph shot straight up, right? We don't know if something like that happens. So this one's a little bit more, we kind of think that it's going to happen this way, but this is a good idea, a good way to get a general idea of how a function works. So remember, when we're talking about limits, we're talking about what is happening to the y values as we get closer and closer to an x value. And if we're looking for a full limit, like a limit like this, it's really two one-sided limits, the limit from the left and the limit from the right. If those two things exist and are equal to each other, then we say that that limit exists and it is that value. So here we would say, of course, that that is 6. Now, we've seen a couple of different ways to do this, but how do we do it if we were just given this and we wanted to algebraically figure it out? Well, that's for another lecture.